Okay, so today's video is continuing to look at graphs of quadratic functions, so parabolas. And today what we want to do is bring together what you looked at over the course of the last two videos, where you looked at the transformations of the parabola. So looked at, what effect does it have when you stick a number 2 in front of the x squared? What does that do to the graph? What effect does it have when you add a 5 onto the x squared? What does that do to the graph? What happens to the graph when you add 2 just onto the x part of the function, so you get x plus 2 all squared? And we looked at those transformations individually. So we looked at y equals ax squared in the part 1 video, and then in the part 2 video you looked at x squared plus c, and you also looked at x plus b all squared. Okay, so what we want to do today is we want to combine those three transformations together to think about the most general quadratic. Okay, so potentially having an a value, okay, which is to do with dilation from the x-axis, reflection in the x-axis, potentially having a c value, which we called it c in the previous video. I'm going to change that to k, just so that we're now looking at the more traditionally understood equation for what we call turning point form. So adding k onto the end rather than adding c, same thing, adding a number on the end. The other thing we're going to look at is potentially adding or subtracting a number b inside the squared function, but in this form we're going to look at today, we're going to change that to h, and we're also going to slightly rewrite the most general form in that we're going to call it x minus h all squared, whereas in the previous video we investigated y equals x plus b all squared. The effect is still the same, we just need to be a bit careful about how we interpret that. Okay, I'm just going to jump across to a graphing program for a minute, just to summarise the things we looked at in the previous video before we move on. Okay, so here we have a parabola. It is, the equation is written over here on the left. It's y equals a times x minus h all squared plus k. So that's that general form, which we're going to call turning point form, which you saw in the notes. At the moment, a is equal to 1, h is equal to 0, and k is equal to 0. So this is the equation y equals x squared. Okay, so what I want to have a look at is just, again, reviewing, sorry, we don't want that one, we want this one. Again, reviewing what happens. So at the moment, if we think about changing the value of a, we already know from our previous videos that making a bigger dilates the graph from the x-axis by a factor of a, so stretches it away from the x-axis. If a was a fraction, it would be also dilated from the x-axis by a factor of a. However, we're going to see that the graph gets squashed because a makes all the y coordinates smaller. If a equals 0, we don't have a quadratic function at all, so that's not relevant. If a is negative, we have a parabola reflected in the x-axis, and if a is anything other than 1, there's also a dilation. Anything other than positive or negative 1, sorry, there's also a dilation happening there. Okay, so then if we have a look at, sorry, just putting this back to a is 1. Then if we again remember what happens with, I'm going to jump ahead to k. So k, remember, as we increase the value of k, simply translates the graph up. If we were to decrease the value of k, we translate the graph down. So that's simply adding or subtracting onto the y coordinate to move the whole graph, not changing its shape, not stretching it at all, just translating it, just shifting it up or down. Now we remember, oh sorry, it's because I changed the step size, my apologies. Okay, now we remember we're calling it h now, we called it b in the previous video. B was to do with translating the graph left or right, and remember that it was the opposite of what we think. So when the equation was x plus 1 all squared, the graph went to the left by 1 rather than to the right with the plus. If it was x minus 5 all squared, the graph would have gone to the right by 5. Now I'm changing the way that we're going to write this general form, so it's not x plus h here, it's x minus h, and this will enable us to more directly interpret that value of h, but we're not changing what's happening here. So for example here, when I make h bigger, h is going to the right, but that's because at the moment h is 2, and that makes the equation x minus 2 all squared, okay, which is to the right by 2. If we make h negative, if we make h negative 1, for example, then when h is negative 1, the equation becomes x minus 1 all squared, so x plus 1 all squared, and the graph has gone to the left by 1. So we're not changing what's happening from what we learnt previously, we're just going to write it slightly differently, and that means that when we write the equation as x minus h all squared, we can more directly interpret, that would mean if h is negative 1, the graph goes to the left by 1. Okay, and that's because in the equation it would be minus 1, which would make it plus 1. I hope that sort of makes sense. We'll go back over to the notes and bring all that together. So obviously we don't need to just change one thing at once. So I can leave h as negative 1. I can make k, you know, positive something, positive 5. And then I could also make a negative 3. No, let's make it negative 2. Okay, and we combine those things together. So now we're looking at a parabola that has been reflected in the x-axis, that's the negative, dilated by a factor of 2 from the x-axis, so a bit stretched, translated to the left by 1, okay, and translated up by 3. The reason we call this turning point form is because you see in this format it's very quick and easy to identify where the turning point will end up. So this graph has gone to the left by 1 and up by 3. The turning point has coordinates of negative 1, 3, which is the h value and the k value. So when we write the equation in turning point form, in this form, h is the x coordinate of the turning point and k is the y coordinate of the turning point. So immediately looking at the equation, the first thing we can identify is the location of the turning point, which is why we call it turning point form. Okay, let's just go back over to the notes now and fill in some blanks over there. Okay, so let's just summarize what we know about a and h and k in this turning point form. So the size of a, so forgetting with not ignoring whether it's positive or negative, but just whether it's a 3 or a 5 or a 7, regardless of whether it's positive or negative, that value. The size of a has the effect of dilating the graph from the x-axis. So the size of a dilates the parabola from the x-axis by a factor of a. Okay, and again, just the size of a, not the, so it wouldn't be a dilation factor of negative 2. If a was negative 2, it'd be a dilation factor of 2. Now, the sign of a, so whether a is positive or negative. So if a is less than 0, so that is negative, then we have, then a reflects, then the parabola is reflected in the x-axis. Oops, so we get an, so we get an upside down parabola. The graph shape is going to go this way. I tend to call that a sad face parabola. Okay, so when the a value is negative, we get a sad parabola. If a is positive, then we get a happy shape parabola. Oh, sorry, other way. H. Now H translates the graph to the left or right. Okay, so H translates left or right. Okay, let's put some examples here so we can be clear about what happens. So if h equals positive 2, that means we have x minus 2 all squared, and that goes to the right 2. If h were to equal negative 3, that means we have x minus 3 plus 3 all squared, and we go to the left by 3. Okay, k translates the graph up or down. For example, if k is equal to 4, that means we get x squared plus 4, which is up 4. If k is equal to negative 5, that means we get x squared minus 5, which means we go down by 5. Okay, so as I mentioned before, this form we call turning point form because immediately h and k tell us about where the turning point will be. If you've taken the parabola which had its turning point at 0, 0, and you've translated it to the right by 5 and up by 3, you now have a parabola with a turning point at 5, 3. So the h and k values give the coordinates of the turning point, or another word for turning point is vertex. So the graph of y equals a times x minus h all squared plus k has a turning point or vertex with coordinates h, k. The graph of y equals a times x minus h all squared plus k has an axis of symmetry, therefore, with an equation x equals h. Okay, so what we have now is a parabola with its turning point at hk, which means the axis of symmetry, that vertical line, is x equals h. X-intercepts are determined by letting y equal 0, same as for every other kind of graph, and the y-intercepts are determined by letting x equal 0 and evaluating for y, same as any other kind of graph. Okay, so we want to put all that together and start being able to sketch graphs of parabolas when they're given to us in turning point form. Alright, so as I mentioned previously, in sketching a graph we must mark the turning point at any x or y intercepts, and there must be a minimum of 2 points including the turning point. Okay, so if the turning point is the x and the y intercepts, we need to mark an additional point, so we've got at least 2 points, one of which is the turning point. Okay, example 1. Sketch the graph of y equals x minus 3 all squared plus 2, clearly labelling the turning point and all axis intercepts with coordinates. Okay, so y equals x minus 3 all squared plus 2. So we want to think about the things that we learn straight away from this. So we learn that there's no reflection, there's no negative out the front here, so the shape is happy. So the shape is going to go this way. We have a happy parabola. Okay. The turning point we can get straight away from here because we can see this minus 3 means the graph has moved to the translated to the right by 3, and this plus 2 means the graph has translated up by 2, and so the turning point has coordinates of 3, 2. The next thing I want you to think about is to combine together these two bits of information to work out, will my parabola cross the x-axis? Okay, so in this instance, if you've got a turning point at 3, 2 and a happy shape, your graph is not going to cross the x-axis. Okay, so we don't have any x-intercepts, and so therefore we don't need to try to calculate them. Okay, I want you to try and, you should only be trying to calculate x-intercepts if there are going to be x-intercepts. If you get to a point where you've tried to solve an equation that doesn't have any solutions, you should have, if your equation was in turning point form, been able to recognise that earlier. So no x-intercept, so we just need to calculate the y-intercept. So y-intercept, we let x equal 0. Now remember the y-intercept, now this is where I really dislike some of the ways that people talk about quadratics earlier and other equations, linear functions earlier. Remember, it's not just the number on the end that is the y-intercept, it is the value of y when x is equal to 0. So when we look at linear graphs, y equals mx plus c, when x equals 0, the number on the end is the y value, is the y-intercept. If your quadratic equation was in this form, when x equals 0, the number on the end gives you your y-intercept. But when the equation is in this form, letting x equal 0 doesn't just equal that number on the end. So I want you to move away from that sense that y-intercept is the number on the end. It doesn't apply for all functions, and it's not correct. So the y-intercept is the value of y when x is equal to 0. So let x equal 0, and then we'll find what y is. So this is negative 3 all squared, which is positive 9, plus 2, and so the y-intercept is at 11. Okay, so we've got all the information we need, and we then want to sketch our graph. So again, don't draw your axes first, calculate your information and work out what you need. Where do you need the axes to sit? What do you need to be able to draw? Okay, so I'm going to put 3, 2, my turning point there. My y-intercept is at 11, which is quite a lot bigger than 2, so it doesn't need to be perfectly precise, but you don't want it to be here, because the suggestion there would be that that distance is 9 and that distance is 2. Okay, your scale's too far out of whack. So you want to make sure that you've got your y-intercept quite high up. Now again, I've talked to you about this before. I wouldn't mark that point necessarily because it becomes hard to miss. I'd probably just think about drawing in my parabola shape. However, sometimes it's helpful to give yourself a rough sense of where you want to hit, because you should then also mark yourself a symmetric point somewhere over here so that you can help to get your parabola symmetric. So what I mean by that is you want at the same height to be the same distance the other side of where your turning point is. Okay, so I'm going to say roughly sort of here is going to give me a nice symmetric parabolic shape. Now remember, we're looking for smooth and symmetric in terms of the shape when you draw it. So if you're not very good at it, use a pencil, rub it out, keep practicing until you get the shape right. So we've got our turning point at 3, 2, we've got our y-intercept at 0, 11, we've got at least 2 points marked including the turning point, and we've got a smooth symmetric shape for our parabola. Okay, let's move on. Question 2. Sketch the graph of y equals 2 times x plus 1 all squared minus 8. Okay, so this time let's think again about first of all the shape, happy or sad. We've got positive 2 out the front there, so we have a happy parabola here. We want to then think about the turning point. The turning point we can see is going to be at negative 1, negative 8. So this graph has moved to the left by 1 and down by 8. So the turning point is at negative 1, negative 8. And then we want to think about, will we have x-intercepts? So if my shape is happy and my turning point is down at negative 1, negative 8, yes, my graph is going to cross the x-axis. Okay. Yes to x-intercepts. So we'll need to calculate those. Alright, we'll always have a y-intercept. The nature of the shape of the parabola will always cross the y-axis somewhere. So we'll always calculate y-intercept. So again, it's not the number on the end. It is the number we get, the value of y, when x is equal to 0. So 2 times 1 squared is just 2 times 1, so it's just 2 minus 8. So negative 6 is my y-intercept. And then we want our x-intercepts. So letting y equal 0, and then we're solving for x. Now when the equation is in turning point form, we're always going to have an equation that we can just solve by rearrangement. So do the same thing to both sides until you get x on its own. So the last thing happening on the right hand side is that subtraction of 8. So we're going to add 8. Then we need to divide by 2. Then we need to take the square root. When we take the square root, we get positive or negative square root. Sorry, I don't need that bracket. Okay, so we get positive or negative 2 equals x plus 1. And then we're going to subtract 1. So negative 1 plus or minus 2. And then we can calculate those two values. Negative 1 minus 2 is negative 3. Negative 1 plus 2 is positive 1. So we've got two x-intercepts, negative 3, 0, and 1, 0. Okay, so we've got all our information. We've got our turning point, we've got our y-intercept, and we've got our two x-intercepts. So we want to think about that information, think about how to draw your axes to fit all that information on. Okay, so I've got quite big negative turning point and y-intercept. Both positive and negative x-intercepts. So we might want to think about, we have 1, negative 2, negative 3. So you do want even spacing between your intercepts. You've got 2 points on the same axis, so they need to be appropriately scaled. So those are going to be my two x-intercepts there. My turning point is at negative 1, negative 8, which is halfway between those two x-intercepts, And then my y-intercept is at negative 6. So if I've put negative 8 here, that's negative 4 there, negative 6 is going to hit somewhere about there. And I might also mark myself a symmetric point over here just to help me get the shape nice and symmetric. Again, make sure your graph has a smooth turning point at the turning point rather than a sharp corner, and extending your graph right to the end of your axis. Oops, sorry, it's a y-axis. Right, that's the point 1, 0. That is the point negative 3, 0. This is the point 0, negative 6, and I've already marked my turning point. Please get in the habit, this question specifies that you should mark the turning point and all axis intercepts with coordinates. Please get in the habit of using coordinates when you label your graph. At VCE level, the exams will always ask you to label the graphs with coordinates, and if you don't use coordinates, they're not correct. Okay, so get in the habit of it now, they'll never be wrong. Alright, example 3, let's do one more. Sketch the graph of y equals negative x minus 5 all squared plus 2. So y equals negative x minus 5 all squared plus 2. Okay, let's think about the shape. So our shape, with a negative out the front here, is going to be a sad parabola. Okay. Our turning point, the coordinates of the turning point, the graph has moved to the right by 5 and up by 2, so the turning point is at 5, 2. Let's think about whether we'll have x-intercepts. So turning point at 5, 2 and sad shape, yes, my graph will definitely cross the x-axis. So we will have x-intercepts. Okay, so we'll have to calculate those. Let's find the y-intercept first, it's easier. So let x equal 0. We're going to get negative 0 minus 5 all squared plus 2. So it's negative 5 all squared. So the negative 5 all squared is positive 25, but this negative out the front means we'll still have negative 25. So negative 23. So y-intercept at 0, negative 23. And then my x-intercepts, we let y equal 0. Oops, sorry, it's minus 5 all squared plus 2. Okay, so at this point we can think about subtracting 2 from both sides, and that would give us, don't write this line for a minute, that would give us negative 2 equals negative x minus 5 all squared. There's absolutely nothing wrong with that. And then we divide both sides by negative 1 and we get positive 2 equals positive x minus 5 all squared. Rather than do that in 2 steps, instead of thinking about subtracting 2 to eliminate that positive 2 from there, I'm going to think about adding x plus 5 all squared to both sides. Okay. And then we're straight away going to keep both things positive. So adding x minus 5 all squared to both sides of the equation gives us x minus 5 all squared equals positive 2, so both sides are positive. We take the square root, which means we get positive or negative root 2, and then x is equal to 5 plus or minus root 2. So there's our two x-intercepts, 5 minus root 2, 0, and 5 plus root 2, 0. Okay, so symmetric about 5, and that makes sense because the turning point's at 5, 2. Okay, so let's think about what we've got here. We've got quite a big negative y-intercept. We're not going to be able to get the scale perfect there, but we certainly want to give that sense that it's a long way down there. Okay, we're going to have 1, 2, 3, 4, 5. So 5, 2, let's keep it pretty close to the y-axis, given that we sort of want, if we want that distance to be 2, we need to be able to mark 23 down this way. So we just want to keep things, it doesn't need to be perfectly measured, but a bit consistent. And then if we think a bit about, again, we don't need to be perfectly precise here, but given that I just drew a scale on the x-axis, I do need to think a bit about where to put 5 plus the square root of 2. Square root of 2 is about 1.4. And so it's going to be 5 plus about 1.4, so it's going to be about 6.4. So it's going to cross somewhere here, and then 5 minus 1.4 is about 3.6, so it's going to be cross somewhere here. So just get a sense of what's happening. Alright, so let's draw in our parabola, and then try and get things symmetric over here. Okay, so something like that. That is the point 5 plus root 2, 0. That is the point 5, 2. That is the point 5 minus root 2, 0. And this is the point 0, negative 23. And there is the graph of my parabola. Okay, the work today is from a worksheet on the turning point form.